Hi, this is John Whitaker from the Probability 1 class, and this is our 20th video lecture. And last time we had discovered a fact about computing the expected value of a random variable using conditional expectations. And I'd like to look at an example of that in just a second. But first of all, the fact in particular that we will be using is the expected value of x is equal to the expected value of x, the expected value of the conditional expectation of x given y. And that's the fact that we're going to be using. And so, as an example, this is something out of our text that says, suppose that the expected number of accidents per week at an industrial plant is 4. Suppose also that the number of workers injured in each accident are independent random variables with common mean 2. Also assume that the number of workers injured in each accident is independent of the number of accidents that occur. Okay, here's the question. What is the expected value for the number of injuries, or of the number of injuries? Of a week. Okay, so in this problem, what we're dealing with is that on average there's 4 accidents per week, and on average for each accident there's 2 people who get injured. And so the question is what is the expected value of the number of injuries per week? And here's the solution. It turns out it's what we would expect the answer to be, I think. So what we're going to do is we're going to let n denote the number of accidents and x sub I, well, that's going to denote the number of people injured on the accident. Let me write that up. XI denotes the number injured in the I accident. Where I is equal to 1, 2, 3. Then the total number of injuries it is a random variable x, which is the sum as I runs from 1 to big N, where N is the number of accidents that occurred, of x sub I. So, what we're looking for is the expected value of x, which will be equal to the expected value of the sum, which we can find by doing conditional expected value. If you will, this is the same thing. Let me back up. This is really, the expected value of x is the same thing as the expected value of x given n equal to little n. Okay, that's by the product. So that's the way I can look at it. And this is what we're trying to find. Now, we know what x is, it's the sum. So let's look at this conditional expectation, and then we'll take the expected value there. Now, the conditional expectation of x given n equal to little n equals to, well, it's the expected value of the sum as I runs from 1 to big N of x sub I, given big N equals to n. Okay. Now, that conditional expectation, we've got at least big N number of random variables floating around, and they're going to be discrete. So we're going to have sum. So it's the sum as x sub 1, sum, x sub 2, sum up to x sub big N of x sub 1 plus x sub 2 plus x sub big N. That's what this is going to be, times, it will be f sub x sub 1, comma x sub 2, comma, all the way up to x sub n, big N, given n, which I'll write down as little x sub 1, it's what it acts on, little x sub 1, little x sub 2, all the way up to little x sub big N, given n equal to little n. Okay, that's what we have. So this is the n sums that we have. Here I have the x sub 1 plus x sub 2 plus x sub n. Here, this conditional probability mass function is going to be f sub x sub 1, x sub 2, all the way up to x sub big N, and then n. of x1, x2, all the way up to x of big N, and then N, all over, this will be F sub N of little n. Now changing these joint probability mass functions and probability mass functions again into what they're defined to be, we have this sum, x of 1, all the way up to the sum of x of n, again here, of x1 plus x2 plus x of n. Okay, this is going to be the probability that x of 1 equals to little x of 1, all the way up to x of big N equal to little x of big N, and big N equals to little n, all over f of big N, or the probability, I should say, that big N equals to this little n. All right. Now, here's what I want to notice. For here we have these big N number of random variables, but we're also assuming, saying, and big N has to be equal to little n. Well, this quality involved in the probability that we're taking affects what's listed here. So I'll rewrite our expression with that effect involved. So it's x of 1 all the way up to x of little n this time. Of x of 1 plus all the way up to x of little n. Of here, this is the probability x of 1 equals to little x of 1 all the way up to x of little n equals to x of little n. And here, n equals to n, all over the probability that big N equals to little n. And now we can use the independence here. And what we're going to get is that's equal to the sum over x of 1's, continue up to the sum over x of little n, of x of 1 plus all the way up to x of little n. This is now using the independence, the probability that x of 1 equals to little x of 1, and x of little n equals to little x of n, times the probability that n equals to little n, all over the probability that n equals to little n. And then this is the sum, as x runs from, x of 1's run all the way up to the sum over the x of n values of x of 1 plus x of n. These would cancel, okay, and we'd just be left with the joint probability mass function for x of 1, x of 2, all the way up to x of n. Okay. All right, and then that can be broken down, if you will, into n sums, where you have the sum over x of 1 up to the sum over the x of n of x of 1 times this joint PDF plus you'd have the next one. So what I'm doing is I'm multiplying this joint PDF times each one of these and then breaking them, breaking these n sums up to n sums. That the last one, this was the first one, the last one will be these n sums, x of 1 up to x of n, and it will be x of n times f of x of 1, x of 2, all the way up to x of n, this joint PDF. And then that's equal to, well, this first sum is nothing more than the expected value of x sub 1. And then this will be plus the next one, I don't have it listed, but will be the value of the expected value of x sub 2 plus, and we have all of this up to the expected value of x sub n. And of course, they all have the same mean here. So if you will, this is n times the expected value of x sub 1. Okay? That's what we have. So as a comment, this tells us that the expected value, the conditional of x given n, okay, is the random variable n times the expected value of x sub 1. That's what we have. Okay? So this is a random, this expected value of x sub 1 is a constant. Here this is, the n is the variable here. So, the expected value of x, okay, which is what we're looking for, is the expected value of x given n. We know what the expected value of x given n is. That's going to be the expected value of n times the expected value of x sub 1. Now the expected value of x sub 1 is a constant, so that's equal to the expected value of x sub 1 can be brought out times the expected value of n. So in our problem, that's equal to, okay, the expected value of x sub 1 I think was 2. 2 people injured per time. And the number of absence we expect per week is 4. So we get 8. That's what we have. Well, this type of random variable is worth noting that we just saw this example of. It's called a compound random variable. And let me put up its definition. So as a definition, the random variable x equal to the sum as I runs from 1 to n of x of I, which is the sum of a random number n of independent and identically distributed random variables that are also independent of n is called a compound random variable. Like to state a fact about compound random variables. says if x is a compound random variable with x equal to the sum as I runs from 1 to big N of x sub I, then the expected value of x is equal to the expected value of x sub 1 times the expected value of n. Okay? And we proved this fact in our solution of the previous problem, where the x sub i's are discrete. Okay. The next thing we're going to do is we will compute the expected value we're going to compute the expected value of a geometric random variable using conditional expectations. Now, just for a second, let me remind you about geometric random variables. That's where a Bernoulli experiment is performed until the first success, and the random variable counts the number of times the experiment was performed. Okay? So, here's our computation. Let's let a Bernoulli random variable a Bernoulli random experiment is what I should say, sorry. Be performed independent times until the first success where the probability of a success that will be designated by a little p, okay, and we're going to let n be the number of trials experience needed the experiment is performed. Instead of writing down the word trials, let's just say times. It's the number of times the experiment is performed. Okay, we're going to find the expected value then. What we're going to condition will we condition it on? When we were working with the geometric random variable, we found that its expected value is going to be 1 over p. And we did it using some derivatives, really, involved in the summation. And it was a little bit messy. But here, we're going to do it a different way with this conditional expectation. And so the first thing we're going to do is we're going to find a random variable y. So we're looking to compute the expected value then. So we're going to start off with let y be defined by 1 if the first experiment is a success. And 0 if the first experiment is a failure. Okay, so here the expected value of n is equal to the expected value of the expected value of n given y equals rho y. Now, y can just be either 0 or 1. And this is going to be a summation over the y values here. So y runs from 0 to 1 of the expected value of n given y equal to y of f sub y of y. That's going to be its definition. Let's expand this. Okay, this will be equal to the expected value that of n given y equal to 0 times the probability that y equals to 0 plus the expected value of n given y equal to 1 times the probability that y equals to 1. Okay. Well, this is equal to the conditional expected value of n given y equal to 0. The probability that y equals to 0 is 1 minus p. Plus the expected value of n given y equal to 1. And the probability that y is equal to 1, the probability that a success on the first trial is p. Now, here's what I want to say. We'll talk about these two conditional expected values. And I'm just going to tell you the expected value of n given y equal to 1. I'm going to try that one first. It's the easier one. So what's the expected value then if we know that on the first time that we're being told that on the first trial we got a success? So how many times did we have to do it with that information? The answer is 1, because we're supposed to do it until we get our first success of the experiment. So that's easy to explain. The expected value of n given y equal to 0, the second part here, that's going to be equal to the expected value of n plus 1. That's what it is. And one way of thinking about that is that if on the first time that you do the experiment, if you're told, well, you didn't get a success, well, then you just start over. And so you say, well, now what's the expected value of how many times it would take us? Well, it would be the expected value of n, except we've got to add 1 to it because we did it once without getting a success. So that's a way of thinking about it. But I'd like to look at this a little bit more mathematically. So, and this one too,
where the expected value of n given y equal to 1, so we'll look at this first. We know that the answer is 1. But what that is the sum is n runs from 1 to infinity of n times f of n equal to n and y equal to 1 over f sub y of 1. Okay, so I'm just going to verify this with our mathematical definition for the conditional expected value, which was n times the f of n given y, which I can rewrite in this form. So here, this is going to be equal to, well, 1 over p, okay, and this will be the sum as n runs from 1. The 1 over p comes from f sub y of 1 being equal to p. Okay? This is n, and this is the probability that n is equal to little n and y equals to 1. Okay, so here, when n is equal to 1, what we're going to get is 1 times the probability of n equal to 1 and y equal to 1. Well, that's going to be 1 times p. And then when n is equal to 2, we're going to have 2 times the probability that n is equal to 2 and y is equal to 1. So what is that saying? That's saying, well, what's the probability that the time that we got the first time we got success was on the second trial, given that the first trial was a success? The chance of that happening is none, because the first trial was a success, so it couldn't have happened on the second trial, or any trial bigger than 1. So really, for all n's bigger than or equal to 2, the terms in this sum are going to be 0. So we just get 1 over p times the first term of this sum, which is 1 times the probability that n is equal to 1, y is equal to 1, which is just equal to 1 over p times, and this is just going to be p. We've got a chance to set it as just 1. So that's how we verify this part. The other part's much harder, I believe. Well, it's harder. But it can be thought of. We'll just start over. If we know we just have one more, then we can start. That's one way of thinking. But using our definition for conditional expected values, here's what we have. I like looking at it this way. That's equal to the sum as n runs from 1 to infinity of n times, again, the conditional probability mass function, which I'll rewrite as f of n equal to n, y equal to 0, over the probability y equals to 0 in this form. This is equal to 1 over 1 minus p. That's probability y is equal to 0. Sum as n runs from 1 to infinity of n times the probability that big N equals to little n and y is equal to 0. Okay. When we let n be equal to 1, we have 1 times this probability. The probability that the first time we got a success was on our first experiment, and that the first experience was a failure. Well, that's going to be 0. Both of them cannot happen simultaneously, so that's 0. So really this becomes 1 over 1 minus p, and when n equals 1 doesn't contribute, we just get 0. So it could be thought of as n equal to 2 to infinity of n times probability that n equals to n, y equals to 0. So here for any n 2 and bigger, the probability that big N is equal to little n and y is equal to 0, well, that's just the same thing as the probability that big N is equal to little n. We know that y had to be equal to 0 in these cases. So that's equal to 1 over 1 minus p times the sum as n runs from 2 to infinity of n times the probability that big N is equal to little n. Okay, here we can do a change of variable. We can let, okay, j equal to n minus 1. When I do, I get, let's write the power out here. we end up getting 1 over 1 minus p. This, remember, we're making this substitution. So j is equal to n minus 1. N started at 2, so j is going to start at 1 to infinity. Here it's going to be, well, j was equal to n minus 1. J is equal to n minus 1. So n is equal to j plus 1. So j plus 1, what n was. And then this is the probability that n is equal to j plus 1. Okay, that's what we have. That's going to be equal to 1 over 1 minus p, sum as j runs from 1 to infinity. Here this is j plus 1. What this is, using the PMF for geometric, that's going to be equal to p times 1 minus p to 1 less than this, so that's just j. I can pull out a 1 minus p, and I get 1 minus p over 1 minus p, sum as j runs from 1 to infinity, of j plus 1 times p to the 1 minus p to the j minus 1. Let's do that. That's equal to 1 minus p over 1 minus p, that's just 1. So here, if I let n be equal to j, I can rewrite this as a sum as n runs from 1 to infinity of n plus 1 p times 1 minus p to the n minus 1. And this is nothing more than the PMF, I should say, for a geometric, okay, evaluated n. So this is the sum as n runs from 1 to infinity of n times, well, n plus 1, here I'll write down, f of n equal to n. So this is the geometric. F sub n of n, I'll write that down like that, which is the sum, if I break it up into two sums, n runs from 1 to infinity, of n, f sub n of n, that's geometric, plus the sum as n runs from 1 to infinity of f sub n of n. That's the sum of the geometric random variable. That's just 1. And this is nothing more than the expected value of n. And that shows the result we wanted. Okay, so we're about to complete the problem. Remember, we're computing the expected value of the geometric random variable. And what we had was so the expected value of this geometric random variable, it was equal to the expected value of n given y equal to 0 times the probability of y equal to 0 plus the conditional expected value of n given y equal to 1 times the probability y equals to 1. Okay, that's where we were. Okay, for this part, we had that was the expected value of n plus 1 times 1 minus p plus, this was 1, this part was 1, and this is p, so that's what we get. So the expected value then is equal to expected value then times the quantity 1 minus p plus 1 minus p plus p. Okay. So this is expected value of n minus expected value of n times p. When I move all of that over here, we're just going to get the expected value of n times p. The expected value of n here and the expected value of n times 1. When I subtract the expected value of n times 1, I get 0. So I add p times the expected value of n, and that's what I get, is equal to 1. And so the expected value of n will be equal to 1 over p. And that indeed is the answer. And that's great. All right. We can use conditional expectations to compute variances. I'll do that with a geometric random variable. As an example, so, for example, for geometric random variable, again, just write it, set up. Suppose, okay, independent trials, each resulting in a success with probability P are performed in sequence. Let n be the trial number of the first success and then he asked to find the variance again. So we're finding the variance of a geometric random variable. Okay. We know that's equal to the expected value of x squared minus the expected value of x to b squared. Okay. And so we can compute each one of these doing a conditional expectation. Okay. And so what we're going to conditional against is, again, we're going to let y be defined as a random variable to be 1 if first trial is success, okay, and 0 otherwise, first trial's failure. Now, here's what we're going to be looking at. The expected value of n squared, which is what we don't know. Here, I mislabeled this. Let me go back very quickly. I wasn't paying attention. This should have been an n. Typo, and this should have been an n. Okay? So both of those were n's to match the variable we're talking about. Sorry. Okay, so this is what we're looking for. This could be the expected value of n squared given y, and it's the expected value of that. So that's how we're doing the conditional. Okay, so expected value of n squared is equal to the expected value of n squared given y equal to 0 times the probability y equals to 0 plus, all right down here, the expected value of n squared given y equal to 1 times the probability that y equals to 1. And that's going to be equal to the expected value of n squared y equal to 0 times the probability that y is equal to 0 is 1 minus p plus the expected value of n squared y equal to 1. The probability of 1 is p. So we need to be worried about these conditional expected values. Okay, the expected value of n squared given y equal to 1. Okay, well, here y equals to 1, that means that we got a success on the first time we did it. So what you expect n squared to be, we expect n to be 1, so n squared's got to be 1. So that's 1. Now, a little bit tougher on this next part. The expected value of n squared given y equals to 0, that part is going to be just like what we did before. It's the sum as n runs from 1 to infinity of n squared. And then this will be f of n y over f sub y of 0. That's going to be equal to f sub y of 0 is at 1 over 1 minus p. This is the sum as n runs from 1 to infinity of n squared times the probability that n is equal to n and y is equal to, here I should have said what it was 0. Y is equal to 0. Okay, again, when n is equal to 1, we're not going to get anything. So this is end up being the sum, has something out front, 1 over 1 minus p, sum as n runs from 2 to infinity of n squared. And here this is just going to be the probability that n is equal to n after that. So look, when n is equal to 1, the chance that we got a success on the first one, and that y was equal to 0 is nothing. So when n equals to 2, the probability that we got success on the second one and the first one was a failure, it's the same thing as the probability we got success on the second one. And that's going to be true for n being 2 and greater. Okay, so this is equal to 1 over 1 minus p, sum, n runs from 2 to infinity of n squared times p times 1 minus p to the n minus 1. And then we're going to let, just like what we did before, j equal to n minus 1. And so I'm going to get as a sum of 1 over 1 minus p. Here this is the sum as n j runs from 1 to infinity. N is going to be replaced by j plus 1, so it's j plus 1 squared. It's just like what we did before. And then this would be p times 1 minus p to the j. Rewrite that. Almost done. Okay, that's equal to, I'll pull out a 1 minus p, and I'll have 1 minus p over 1 minus p. Sum as j runs from 1 to infinity of j plus 1 to b squared. This will be p times 1 minus p to the j minus 1. That is the probability mass function. So this is going to be equal to the sum as j. Well, let's make a change here. Let's let n be equal to j. And so we have, this is 1, this is sum as n runs from 1 to infinity. Here this will be n plus 1 squared times f sub n of p, and that's just equal to the expected value of n plus 1 squared. Okay, that's what that is. Okay, and so we could rewrite this, well, we'll put a big N. Biggie. So, the expected value of n squared, that's going to be equal to, it's going to be, from our previous work, it's going to be the expected value of n plus 1 to b squared times 1 minus p plus, it was the expected value, no, it'd just be plus p. Okay. So that was from our previous work where we had done the calculation for the expected value of n squared by the expected value of the conditional expected value of n squared given y. Okay? And that's what we get. And this is equal to, here, this is equal to the expected value of n squared plus 2 times the expected value of n plus, that would be 1 squared, the expected value of 1 would be 1, all that times 1 minus p plus p. Get. Okay. So what we have is the expected value of n. That's going to be equal to the expected value of n squared times 1 minus p plus 2 times the expected value of n times 1 minus p plus 1 minus p plus p. Okay. And this is the expected value of n squared. I wrote down the wrong thing. And that means the expected value of n squared is equal to the expected value of n squared minus p times the expected value of n squared. This is plus 2 times, we've already calculated this, 1 over p, times 1 minus p, and then this is plus 1. So when we subtract this, we get nothing. When we add this, we have p times the expected value of n squared is equal to 2 minus 2p over p plus 1, which is the same thing as p over p. So p times the expected value of n squared is going to be equal to, this is going to be 2 minus p over p. So the expected value of n squared is going to be 2 minus p over p squared. Thus, the variance of n is equal to the expected value of n squared minus the expected value of n to b squared. That's going to be equal to this, 2 minus p over p squared minus 1 over p squared, which is equal to 1 minus p over p squared, and that is what the variance of a geometric random variable is. Okay, ladies and gentlemen, that should be enough for today. Thank you very much for your time and patience.